students. So up until last class we looked into the concepts of changing the variables in a double integral. We also learnt about Jacobian transformation. So we actually looked into the fact that if we have an integral of let's say integral fxy dx dy, where the integration is on certain region E, then by using some sort of transformation we can be able to transform this surface integral to a region E1, and here we will have f of uv, then Jacobian, and then du dv. So we can change the variables of the integrand, and by doing this change of variables it will actually make our life a little bit easier, because the transformed integral, there is a strong possibility it can be a simpler integral, and then it will be easy to compute this integral than computing this difficult one. And of course we have to find out the range for this integration, so it will change accordingly based on the transformation, and then we just we just calculate the Jacobian, and then we calculate this integral, and in most of the cases this actually comes out to be a very simpler integral to compute, and the answer would exactly be same. Now besides change of variable of integral, sometimes it's also wise to change the order of integration. So suppose if we have a range of let's say x running from a to b, and then y is running from some function of x to some function of x, fxy dx dy. So it can be possible that this integrand is so it can possible that this integrand is so complicated, or how to say, not so common, that that we cannot integrate it properly. So it's not falling into one of the traditional how to say integral calculation. So we cannot simply do the integration here. One such example could be, let's say we have example we have something like this integral 0 to 2. So x is running from 0 to 2, y is running x is running from 0 to, y is running from 0 to 2, and x is running from y to 2 e to the power x square dx dy. So now this integral, let's say for example here the integrand is not so common, because in order to integrate this, even with respect to x, or with respect to y, I mean with respect to y it will be easy, but with respect to x we don't have any antiderivatives here, or we cannot express e to the power x square in some method of substitution way. So calculating this integral will not be straightforward, and then the only option we will have is to transform this integral into a simpler integral by doing the change of order. So if by doing the change of order, if we can be able to obtain a rather simpler integral, then that can be evaluated, and of course the value of those two integral would be same. So this is one such scenario. Now let's work out an example where we can see that by changing the order of integration we will still obtain the same answer. So let's start with the following example. It says find the area between the region x square equals to y and y equals to 2 minus x. So we have to calculate the area between these two curves. So as I always say, it is always suggestible to draw the area first. So let us draw. So this is our x, this is our y. So we have x square equals to y, so it should be something like this, a parabola passing through origin, so it must touch the origin as well. All right, and then we have x plus y equals to 2. So let us draw this line as well. So it must look something like this. So this is my line x plus y equals to 2, and this is my parabola x square equals to y. So this is the area bounded between them. Let's call this as point O, then this is A, this is my B, this is C, this is D. Now since the parabola and the straight line, they are intersecting, or the area is bounded between them, so they must meet at some point. So in order to calculate that, we have here the parabola x square equals to y and y equals to 2 minus x will meet at the following points. So how do we calculate? We just substitute y equals to x square in this equation, so it will be 2 minus x equals to y equals to x square, and therefore this will become x square minus plus x minus 2. So the roots of this equation will be x equals to, we can factor it, and then it will be x equals to 1, and another root will be so another root will be I can substitute x equals to 1, so one root is 1, and another root will be, if I substitute 2, then this will be 4, so another root will be minus 2. All right, so I have minus 2 here, and I have 1, let's say 1 here. So they are meeting at the point, x coordinates are minus 2 and 1, and when x is minus 2, then y is 4, and when x is 1, then y is 1. So that means they are intersecting at the point 1 1. So they meet at 1 1. All right, and minus 2 comma 4. So these are the 2 points they are meeting. Now let's calculate the area in this way. So we first integrate. With respect to y, and then with respect to x, and then with respect to x. So that's how we are maintaining the order. So if we integrate with respect to x later, so then in that case x will vary from minus 2, so we can write simply minus 2 to 1, and y we can write, so y, the area bounded between these two curves. So for these two curves, x is varying from minus 2 to 1. All right, so that's the range for x, and for y is varying between these two curves. So that means it is above this parabola, but below that straight line. So it is above the parabola, below the straight line. So above the parabola, that means we have x equals to y equals to x square, and below that straight line is 2 minus x, dA. A denotes the area. So now we have x running from minus 2 to 1, and x square running from 2 minus x, and we are integrating with respect to y first, and then we are integrating with respect to x. So that's what we are doing. So if we integrate with respect to y first, then we'll end up with integral minus 2 to 1 y. So integral with respect to dy, so y, and then ranges would be x to x squared to 2 minus x dx, and then we substitute the value. So it will be 2 minus x square. So 2 minus x square dx, and after integrating and substituting the value, we will be able to obtain 9 by 2. So ultimately 4 by 5. So that's the area bounded between these two curves. And not only that, we integrated with respect to y first, and then we integrated with respect to x. So that's the order we followed actually. So alternatively, now let's change the order. Alternatively, let us change the order of integration That means, we integrate with respect to, so we integrate with respect to x first, and then with respect to y, So what will happen? Is the following. So we still have, let's say, integral over the region E. I am calling this region. So I am calling this region as E. Now, if we want to integrate with respect to x first and then with respect to y, we have to see how x is varying. So first of all, they intersect at the point x equals to 1, y equals to 1. So let us draw a line parallel to x axis. So this is my straight line y running from y equals to 1. So now here we can see that x is varying from so here we can see that y is varying from 0 to 1, right? So y is varying from 0 to 1, and x will vary from this corner to this corner. So that means minus square root of y to plus square root of y. So y is from 0 to 1, x is from minus square root of y to plus square root of y. So let's write it. So we separate the integral into these two subregions. So this is my first subregion. Let's mark this way, and this is my second subregion. This is the second subregion, and this is the first subregion. All right. So we will write here dA. So we will write it as integral from 0 to 1, that's for y, and integral x running from minus square root of y to plus square root of y, and then this is dx dy. Now we are in this region. So in this region, y is varying from 1 to 4, right? So y is varying from 1 to 4, and x will vary from y equals to minus square root of y to this line, right? Because that's where the x is bounded. So we will now write y is varying from 1 to 4, and x is varying from minus of square root of y to 2 minus y dx dy, and then we calculate. So if we calculate, then we have basically integral y running from 0 to 1, then we have dx dy. So we will have x, and then this will be minus of square root of y to plus of square root of y dy, plus integral from y running from 1 to 4. We integrate with respect to x. So we integrate with respect to x, and then this will be x, then minus of square root of y 2 minus y dy. So if we substitute, then this will be y running from 0 to 1. This will be square root of y. So basically 2 square root of y dy plus integral y running from 1 to 4, 2 minus y minus plus square root of y dy. So if we integrate, then ultimately here also we will obtain 9 by 2. So 4 by 4.5. So we saw that just by changing the order of integration, we don't get different answer, because the area where we are actually doing the integration is fixed. It's just that we are changing the order of integration. That means instead of integrating with respect to x first, we are integrating with respect to y, but that will not alter the value of the overall integral, because then in that case we are getting a different area, which is not which will not be the actual area bounded by the curve that was given to us originally. So even if you do the change of variables or change of order of integration, the area of the region bounded by these two curves or the integral which you are evaluating has to be same, and it is same all the time. Now we see that sometimes we come across with integrals which are really difficult to evaluate, and then just using this tool, that is changing the order of integration, we might end up getting a little bit easier integral to evaluate. For example, in this case we had to evaluate the area bounded between these two curves. So you see, if we are integrating with respect to y first and then integrating with respect to x, then we are calculating a very simple integral, and that's the answer. But if we change the order of integration, then in that case we are basically calculating two sub integrals, so this one and this one, and we also have to do some how to say, some effort to basically calculate these two domains. So sometimes it is useful, sometimes it is not. It's just that it's from the intuition. You have to understand whether the integral can be integrable or not, and then we use the tool. We will work out one or two more examples just to make the idea clear. So let's look into another example. So example 2, calculate or evaluate integral from 0 to 1, integral from 0 to 1 minus x. So this is basically for x and this is basically for y, cos of 1 minus y whole square dy dx. So now solution. First of all, let us draw this region. Y x 0. So here our x is running from 0 to 1 and y is running from 0 to 1 minus x. So it's basically a straight line, x plus y equals to 1. So let us draw that line. So this is that point of intersection, 1 1 1 0, and this is 0 1. All right. So that's basically our given region of integration. So I'm calling it as E. This is my point A and this is my point B. So here just looking at this integral, let us write it as I. It's very straightforward to see that it's not possible to integrate this, because even if you want to substitute 1 minus y square equals to some z or something, then in that case this cos of 1 minus y square dy, it cannot be reduced to a very simpler integral. So this is quite how to say, a complicated form, although it looks simple, but it's not very easy to integrate this. So then in that case the only way out we have is to change the order of this integration and see whether we can do something about this integral here. So first of all, if we change the order of integration, so what will happen? So changing the order of integration. So first of all, we write the area, the region of integration order of integration y, the region of integration lies in the strip between x equals to 0, x equals to 1, and is determined by y values starting at 0 and increasing to the line y equals to 1 minus x. So that's the area of integration or region of integration. Now we see that if we instead of instead of integrating with respect to y, if we integrate with respect to x first, then in that case the same region, in the same region our x will vary from then 0. So x will start varying from 0 to 1 minus y, and y will vary from again 0 to 1. So it's not really changing the limits here. So if we change the order, so changing the order of integration, our I will look integral x running from 0 to 1 and y running from 0 to 1, and x will run from 0 to 1 minus y, because the integrand would remain same. It's just that we have changed the order. So if we change the order, then in that case, since here we don't have two sub regions like parabola and straight line and all that, here we just have this straight line and the usual coordinate axes. So it's very easy to calculate the range for x and range for y. So now we have cos of 1 minus y square dx dy. So when we integrate, then it will be integral 0 to 1. So y running from 0 to 1 cos of 1 minus y square, and then here we will have integral x running from 0 to 1 minus y dx and then dy. So this will be 1 minus y times cos of 1 minus y whole square dy, y running from 0 to 1. Now we can substitute this 1 minus y equals to z. So now we can substitute 1 minus y square equals to z. So then this will be 2 times 1 minus y dy equals to minus of dz. And if I substitute the value, so when y is 0, z is 1, and when y is 1, z is 0, and here I have minus, and this will be sin z dz, and since we have minus here, so we can change the limit. So sin z to z equals to 1 sin z dz, and then this will be cos z running from 0 to 1, it will be cos 1 minus cos 0. So basically cos of 1 minus, so it will be minus cos 0 minus cos 1, basically 1 minus cos of 1. So that will be the there is a half here, so of course there will be a half here, so half, and then we will have minus 1 by half. So 1 by half minus, and then this will be 1 by 2. So this is basically cos z, and cos z is sin z, so we will not get any minus here, and then this will be sin z, this is plus, so this will be sin 1, so this is sin 1 minus sin 0, so ultimately we will get half of sin 1, right? So we won't get these. So half of sine 1 is the required answer. So just in this example also we saw that, so this is basically a, how to say, calculation error. I know, I'm pretty sure you can be able to fix that. So here in this example also, initially if we look at the problem, it's very clear that we cannot be able to integrate this function with our traditional method, because there is no dz, there is no, how to say, that antiderivative form here. So we cannot substitute 1 minus y square and get something, so get something compensated from here or something. So then in that case we have to, the only option have is to change the order of the integration. So if we are changing the order of integration, then we have to find the range for the variable x and y. So that's what we did. And another good thing about this example was x was running from 0 to 1 minus y, as y was running from 0 to 1 minus x. So it was fairly easy to calculate the range for the variable x, and for the variable y it's just interchanging. So now y is varying from 0 to 1. So that's what we have written here. All right. And if we have that, so then in that case we integrate with respect to x first, and then we can have, now we have that z, how to say, method of substitution formula working. So we substitute 1 minus y square equals to z, and then we just do some simple calculation. So that's what your answer is. So this is one such example where, how to say, changing the order of integration made our life a lot easier actually. Now it may be possible that sometimes changing the order of integration may not be that useful. So what I mean by that is, let's consider another example. Let's consider another example. So here we have our area of integration as 0 to, so x is 2 and y equals to x. So this is my y equals to x, and this is the area of integration, right? So E. So this is my area of integration, and so after changing the area of integration, we can write I equals to we can write I equals to 0 to 2. So y would still be varying from 0 to 2, right? Yes. And then x will vary from 0 to 2, yeah, and then y will vary from x to 2, and then we have e to the power x square dy dx. So if we have done that, then in that case it will be when we are changing the order of integration, then y is varying from 0 to 2, and x is varying from 0 to 2, and y will vary from, so y will vary from 0 to x. Yes, so y will vary from 0 to x. So now we can be able to integrate this integral with respect to y first. So if we want to integrate, then this will be integral x running from 0 to y, and then this will be dy. So substituting x, then it will be x e to the power x square dx. Now we can substitute this, and then we get the value out of it. However, if we had started with, let's say, if we have started with, let's say, instead of this, we can have a problem where we can start with, let's say, this example. If we had integral I equals to y running from 0 to 2, and x running from 0 to 2, and y running from x to 2, e to the power x square dy dx, and x running from y running from 0 to 2. Where is that? So if we have started with y running from 0 to 2 and x running from let us change this. So x running from 0 to y, then in that case, if we change the order of this integral, it would converge to integral y running from x running from 0 to 2, and y would run from x to 2 e to the power x square dy dx, and then this will reduce to integral from 0 to 2 e to the power x square minus x e to the power x square dx, which is a rather complicated integral to evaluate than evaluating this integral. So just starting with a different form of integral, we can be able to see that always changing the order of integration may not help. So sometimes it is useful, sometimes it is not, but most of the time it is useful. So as in this example, it becomes rather complicated to integrate, especially the first term. So sometimes we don't have to change the integral, but most of the time we do. So we will conclude this section here today, and in the next class we will start with area and how do we calculate the area of under a curve, and several other things related to area, volume, and surface integral. And we will work out more examples based on this topic in our assignment assignment sheets. So thank you for your attention today, and I'll see you in the next class.